Hello, so today we are going to do this problem, which is part of August challenge, unique paths. So the problem says we have a robot on an n by n grid, and the robot is initially located at the top left corner, right? And so the robot tries to move to the bottom right corner, so we go from the start to the finish. And the finish line is basically n-1, n-1, right? It's the last position. And we can only move down or right. So the possible moves are either right, like this, or down. Okay, we can't move left, we can't move up. And we get two integers. We get basically the size. And the goal of the problem is to return the number of possible unique paths. So that the robot can take to get from start to finish. Basically, the last one just says that the answer will be less than or equal to this number. Not really a big deal. So for example, if m equal to 3 and equal to 7, like this example here, we have 28 ways. So you can think maybe the robot goes here and then like this. That's one path. Another path maybe like this, another path maybe like that, so you get the idea. So let's start solving this problem. So number of unique paths, this makes it seem like dynamic programming. Maybe we can do just recursion with memoization. So let's see how we can solve it. So the easiest way is just to do a DFS, right? And basically start from this position, which is 0, 0, and just do a DFS to go to all positions. And when you reach this position, which is, I will call MR because it's the number of rows, and NC just to make it clear. So this one here would be R-1, C-1. So once we reach this position, we can return 1, saying that that's one path, right? And now we can just explore with our DFS all the possible positions. We could go like that, and every time we reach this position, we can return 1, right? And so for each, the only thing we need to remember with DFS, since DFS we go from one node to its neighbors, since we can go either only down or right? So we would have to only explore these two neighbors. And so going down is just, if this was the position ij, going down is I plus 1 j, and going right is I j plus 1. And so we need to traverse these two neighbors. We just need to make sure we don't go out of boundaries. So we need to test for that. Now one other thing is that arriving at this position, calculating the number of paths from this position, once we calculate it, it's the same no matter if we arrive at this position from here or if we are, that wasn't a nice example, but for this position, right? Let me just clear up this. So for this position, no matter where we arrive at it, if we arrive at it like this or like this, the number of paths from this position is still the same. And so we don't need to recalculate it each time. So what this would mean is that for our DFS, we need to cache the unique path from a position ij. So with recursion, we could do that with memoization, and then after that, we can see if we can apply dynamic programming. So that's the main idea. Now let's jump into the code. Okay, so let's write down the solution. So we said we need DFS, so let's define our DFS function. So it's from a cell ij. And initially we want to call it on the first cell, which is 0, 0. And we said if we reach the end, which is the end position, the finish position, which is R-1, C-1. So I equal to R-1 and G equal to C-1. And let's rename these just to make this easier for us. This is number of rows, this is number of columns. And now we return 1 because we reached a path, a valid path here. And then we start counting and visiting the neighbors. So I'll note the neighbors by ni and j. And as we said, you can only go down or right, which is ij plus 1. And now what we need to do is check if we are still within the boundaries. So it's a valid position first. That's just for I, and for j is within 0 and c. Okay, if that's the case, then we want to do DFS on the neighbor. Now the neighbor will return us the count, and so we need to add that to our overall count for I, right? So the count equal to 0, and all basically the paths from the neighbors, right? That will be the paths to the ij, right? So we want to do count plus here, and then at the end it's count. So all the path from the sum of all of the paths from its neighbors, that's those are the paths from it, right? And now that's pretty much it. So that's without memoization. Let's just run it, make sure it passes the basic test cases. And that does. Now we need to do memoization. So what we can do is just have a map like this, and set the map for ij to equal to the value. And here we want to check if ij is in that memoization table or map, we want to return it. So we can just return it like this. And now that should be it, right? We memorize it. If it already exists, we don't calculate it again. So let's run this again. And let's submit. Okay, so that passes test cases. Now in Python, you don't actually need to create your memo table yourself. There is a nice way to do it, so we can just remove memoization hash map that we have here. And we could just use, in Python, we could use cache or RU cache, whichever you want. And that will, by definition, that will just like do the same memorization we did for you. So let's run this. Let's submit. And that passes test cases. Now, so this is the recursion with memoization, but we can also solve it with dynamic programming. So let's see how to do that. Okay, so how can we solve with dynamic programming? So with dynamic programming, what would be our state? That's something we need to think about here. What's the state we are looking at? So for dp of ij, this is just basically the number of unique paths to get to ij from 0, 0, right? What this would mean is that the goal that we are after is just the number of unique paths, right? To get to r-1, c-1, which is the finish from 0, 0, right? And so that's just dp of r-1, c-1. So we know what we are after, right? Now, how can we get the recurrence relation? So our recurrence relation actually is pretty simple. We know that for a node, for a position, you can either go right or down, right? So if we take a look at this, you can either go down like this or right, okay? So what this would mean is that dp of ij is just the sum of the paths. To get to this point, you just need how many paths did you use to get to this point and how many paths you use to get to this point, and then we can just sum these up. Same thing here, for example, it's the number of paths to get from this point and the number of ones you get to this point. It's just the sum, right? Because if let's say you have three ways to get to this position here, right? Let's say 3 and 2 here. Well, the number of ways to get to this one is just 3 plus 2, because you could either do all the 3 ways and then just go down, or all the 2 ways and just go right, okay? And so that's pretty much it. So what this would mean here is that for our solution, for our recurrence relation here, is just dp of I minus 1. That's this position here. That's this position here. So this is I minus 1j, and this is I j minus 1. and this is dp of I j minus 1. Okay, so that's our recurrence relation here. And now the only thing left is what's our base case. So for our base case, it's the dp of 0j for any j position, and dp of I 0. What does this mean? So this is the number of paths to get to from 0, 0 to 0g. And this is the number of unique paths to get from 0, 0 to I0, right? So what does this mean? Let's clear this up. So this is row 0, and this is column 0. So basically, it's what are the values in this column and in this column, and in this row and this column. Now, if we take a look here, the only way to get from this position to all of these is to go right, because you can't go up. If you went down, you can't go up, right? And for similar thing for here, for the column, is that you can only go, so you can only go down, because you can't go right and then go down and then go left. You can't go left to go back to it. So the only way for each of these two is to either go right for the row 0 or to go down for the column 0. What this would mean is there is only one unique way. Okay, so what this would mean is for our dp table, this is actually all 1, and this is all 1. So for all j's, dp of 0j is equal to 1, and for all i's, dp of I0 is equal to 1. And so this is our base case. So that's pretty much it. Now we have our recurrence relation, we have our base cases, we know what's the goal value we need to return, which is this here. Now we can write our dynamic programming solution. So let's do that. Okay, so let's write down the dynamic programming solution here. So what we said was that we need to have our dp table first. So our dp table, we just initialize it to 0 for all values. Now we need to go and initialize our base case. So our base case is for the first row, which is going to be, sorry, for the first row, where every value needs to be 0. And then for the first column, where every I0 needs to be equal to 1. So that's our base case there. Let's just arrange this a little bit like this. And now we can do our, I'll fill this up in a second. We need our recurrence relation here, where we said that dp of ij is equal to the previous row at the same position. So going the position where we go down and the position where we go right. So which means the position on the top and the position on the left. So the number of unique ways to get to each, the sum of that. And here, well, we need to definitely get to R, and we get to at the end of the columns. One thing though is that because this is I minus 1, if we do 0, we will get to -1 here, which is not valid. The other thing is also we already filled I0 and 0g, so we can start from 1 here for each. And at the end, the goal that we want to return is just the value at the last position, right? So that's this. And this should be pretty much it. So let's run it and let's submit. And that passes test cases. Now, in terms of time complexity, we are doing O of R plus O of C plus O of R by C. So in terms of time, it's O of R multiplied by C time. In terms of space, we are using this dp that has the size R by C, so also RC space. Now, one thing you may notice is we actually don't need an R by C table. We can reduce the memory or space we are using here, because if we take a look here, every time we only need I minus 1 and j minus 1. So we need the previous, or the value in the previous row at position j, and the value in the current row at position j minus 1. So we only need the previous row and the current row, right? So let's just have one table to save the current row and one table to save the previous row, and that should be all we need. So we can make this be the current row, right? dp, so this would be the current row, and we can have prev be the previous row, right? So initialize it to the same thing. So this is the previous row. Now, how do we initialize these two? So dp of 0 is going to be 1, right? The current row, first position, there's only one way to get there. And then the previous row, 0 is also 1. So yeah, basically just replacing this logic. And now we can, here, this is actually just dp of j, the current row at position j, and this is the previous row, so prev at position j, and this is just the current row at position j minus 1. And now what we need to return is just the current row at position, the last position. That would be the finished position in the problem. And one thing to note is that actually now, since we are not using I minus 1, we can have our loop start from 0. Okay, so let's run this. Yeah, so one thing we didn't do here, which is we need to, after the iteration and filling the current row, for the next row, prev needs to become the current row, right? So we take a copy and assign it to it, because otherwise it's always the first row, okay? So let's run this. And let's submit. Okay, so that passes test cases, and it actually gets us down from O of RC to just O of 2 C's, right? This one and this one, so just O of C space. Okay, so one thing you may even realize is, well, the previous row, we are just assigning the dp value, and for each j, we haven't replaced that j value. And so we don't need to store a previous row. We can just use the whatever was in the previous position at dp of j and get rid of this and get rid of this row here. And this is just plus like this, okay? So yeah, that makes it simpler, but still O of C space. So if we run this, and submit, that passes test cases as well. Yeah. Yeah, so that's pretty much it for this problem. Thanks for watching, and please like and subscribe, and see you on the next one. Bye.